Good day, learners. Yeah, welcome back to our chemistry class. Today, we are going to be learning Dalton's law of partial pressure. John Dalton, as most of us have known, was the originator of atomic theory. But he also studied the physical behavior of gases when they are in mixtures. This behavior of gases led to the theory called Dalton's law of partial pressure. Just before we dive into this topic properly, if you are a new member of this channel, kindly subscribe to my channel and click the notification bell for my subsequent content. And don't forget to share and leave a comment as you leave. Now, Dalton's law of partial pressure. As we said, John Dalton studied the physical behavior of mixture of gases. But in this case, these gases do not react together. Dalton's law of partial pressure states that the pressure exerted by a mixture of gases is equal to the sum of their individual partial pressure, provided that the gases do not react at that temperature. This definition or this law is talking about gases that are not reacting and they are in the same confined area. If a gases is in a container individually, it's going to exert a pressure. When we have gases this way, this gas collide with one another and also collide with the wall of the container. When this gas, let's say this gas is nitrogen gas, the gas is exerting its pressure onto the wall of the container. We call it a pressure. But when we now have a gas, we have a mixture of gases here, say nitrogen and oxygen. This mixture do not react. Let's say we have nitrogen and hydrogen. This mixture do not react in this place. Since they do not react, each of these gas exerts its own pressure on the wall of the container. Then we call it a partial pressure. So partial pressure of nitrogen and also partial pressure of oxygen. Now, the total pressure in this case will now be equal to the sum of the individual partial pressure. That is, total pressure equals to pressure exerted by nitrogen plus pressure exerted by oxygen. So when we have more than two gases in a container, individual will exert its own partial pressure onto the wall of the container. We say total pressure will equal to P1, that is first gas, plus P2, plus P3, plus T, we get to the end, Pn. So where n is a whole number or is a gas which which is not determined now. Let's look at the next subtopic, gases collected over water. During the preparation of some gases like hydrogen, chlorine, oxygen, and many other gases like HCl, after the production of these gases, they have been collected over water. When these gases are being collected over water, they become wet. Now, since these gases is being collected over water and they become wet, the total pressure in this case is going to be the pressure of the gas and the pressure of the water vapor that will be released in that aspect. So which means that we have total pressure is going to be equals to pressure of the gas plus pressure of the water vapor. So the wet gas that is being produced before it can be used, it has to be dried. Maybe it should be passed through a drying agent. But according to the that is total pressure will equals to pressure of the gas, that's the partial pressure of that gas plus the partial pressure of the water vapor. From here, we can get the partial pressure of gas to be equals to, when you take this one here, we have total pressure minus partial pressure of water vapor. Now, let us now look at the application of this. Example 1. 20.0 dm cube of hydrogen were collected over water at 70 degrees Celsius and 79.7 kilonewton per meter square pressure. Calculate question A, the pressure of dry hydrogen at this temperature. If you look at this question, you are given the volume of hydrogen that was collected over water at this temperature, 70 degrees Celsius, and 79.7 kilonewton per meter square. But this hydrogen it was collected over water, and the vapor pressure of water at that when it was collected over water, the vapor pressure is 1.90 kilonewton per meter square at that 70 degrees Celsius. Meaning that this 79.7 kilonewton per meter square cannot be used as our pressure of hydrogen. Rather, we have to take away the vapor pressure according to Dalton's law that states that pressure P total is equals to pressure of gas plus pressure of water vapor. Our gas now is hydrogen. P total is equals to pressure of hydrogen plus partial pressure of water vapor. From here, we can get the pressure of hydrogen by taking this one away. So pressure of hydrogen will equals to total pressure minus pressure of water vapor. So from here, our pressure of hydrogen will equals to total pressure here, we have 79.7, that is kilonewton, minus 1.90 kilonewton per meter square. Now, what do we have here? When we take it away, we have 77.8 kilonewton per meter square. So that is the pressure of hydrogen. That is question A. So this is question A. Question B. Calculate the volume of dry hydrogen at STP. If you could recall, we've dealt with the meaning of STP and how to go about its standard temperature and pressure. Now, let's now go back. 20.0 dm cube of hydrogen. That is volume of hydrogen, V1, 20.0 dm cube, were collected over water at 70 degrees Celsius. Our T1, 70 degrees Celsius, which has to be converted to Kelvin. So we have 290 Kelvin and 79.7 kilonewton per meter square. So this is now our pressure. The new pressure now of that hydrogen gas is 77.8. Pressure P1, 77.8 kilonewton per meter square. Don't forget that kilo means 1,000. Kilo means 1,000. That is 77.8 multiplied by 10 raised to power 3 Newton per meter square. Fine. We are now told to calculate the volume of dry hydrogen at STP. When STP is mentioned at the end of the question, you know, your P1 is going to be your standard pressure. And the standard pressure, 1 atmospheric pressure is given as 101.3 kilonewton per meter square. That is times 10 raised to power 3 Newton per meter square. And your T2 is going to be your standard temperature, which is 273 Kelvin. Then our V2 is what we are looking for. Now, if we look at this, this is a general gas equation. P1 V1 over T1 is equals to P2 V2 over T2. So from here, we can get our V2. V2 will equals to P1 V1 T2 P1 V1 T2 divided by, since you have removed this, we are going to have P2 and T1. Now we compute our values. Our P1 here is 77.8 times 10 to the power 3 multiplied by our V1 20 multiplied by our T2 here 273 divided by our P2 second pressure. This is our P2, don't forget, sorry, P2, which is 101.3 times 10 to the power 3 multiplied by our T1 290. So this goes in this. So we have to multiply the numerator and divide it by the denominator. So try to solve it and tell me what we have. Our values is 14.46, which can be approximated to 14.5 decimeter cube. It's in decimeter cube because our initial volume here, V1, also is in decimeter cube. Example 2. Two flasks were connected by a narrow tube with a closed tap. One flask contains 300 centimeter cube of oxygen at 1.0 times 10 to the power 5 Newton per meter square, while the other contains 200 centimeter cube of nitrogen at 2.0 times 10 to the power 5 Newton per meter square. Figure 8 below shows the diagram. So this is the diagram of the tubes. Here we have 300 cm cube of oxygen here. Here we have 200 cm cube of nitrogen while the tap is being closed. After opening the tap, calculate A. Partial pressure of each gas. B. Total pressure of the mixture at constant temperature. One thing is, when you open this tap, oxygen has to mix with nitrogen. But that does not mean they are reacting, but they are in a mixture. We must know their total volume. Total volume, V total, will equals to 300 cm cube plus 200 cm cube. So 300 for the oxygen and 200 for the nitrogen. We have 500 centimeter cube. So we are told to find the partial pressure of each gas. First of all, partial pressure of oxygen. We have to calculate partial pressure of oxygen. Now let's go back. Two flasks were connected by a narrow tube with a closed tap. One flask contains 300 cm cube of oxygen. Volume of oxygen, let's say V1 for oxygen, 300 cm cube at 1.0 times 10 to the power 5 Newton per meter square. P1, 1.0 times 10 to the power 5 Newton per meter squared. While your V2 is the total volume when they mixed. That's the 500 centimeter cube. Then your P2 is unknown. So this is the partial pressure we are looking for now. The partial pressure for that what? For the oxygen, the first gas. If we have P and V, that is Boyle's law. That says P1 V1 equals to P2 V2. So P2 equals to P1 V1 over V2. So what's our P1? We have 1.0 times 10 to the power 5 multiplied by our V1, 300, divided by my V2, which is 500. So let us divide this. So we have 60,000 P2 Newton per meter square, or P2 is equals to 6 multiplied by 10 raised to the power 1, 2, 3, 4. 10 raised to the power 4 Newton per meter square. So this P2 now is the partial pressure of oxygen gas. Now, let's now move on to that of the nitrogen gas. Going back to the question, two flasks were connected by a narrow tube with a closed tap. One flask contained 300 cl of oxygen at this pressure, while the other contains 200 cl of nitrogen. Now, for the volume of nitrogen, V1 for nitrogen equals to 200 centimeter cube at the P1 is 2.0 times 10 to the power 5 Newton per meter square. The V2 will now be our total volume that we calculated here, 500 centimeter cube. Then our P2 is the partial pressure of the nitrogen, which is unknown. According to what we did there, that is Boyle's law, P1 V1 equals to P2 V2. My P2 will now equals to P1 V1 divided by my V2. From here, my P1 here, we have 2.0 times 10 to the power 5 multiplied by my V1, 200, divided by my V2, 500. So, when we go by this, what do we have also? We have 80,000 Newton per meter square. Therefore, the partial pressure of that nitrogen will be 8 times 10 to the power 4 Newton per meter square. So that is for question A. Now question B, we are asked to find the total pressure. And don't forget your total pressure will equals to the sum of the partial pressure of oxygen and that of nitrogen. So question B, total pressure will equals to partial pressure of oxygen, that's our P1 for this P2 here, plus partial pressure of nitrogen, the one we got earlier, that's 80,000. So we have, for oxygen we have 60,000, plus for nitrogen we have 80,000. So when you sum up this, we have 140,000. That is, we have 1.4 times 10 to the power 1, 2, 3, 4, 5 10 to the power 5 Newton per meter square. So this is how to apply Dalton's law of partial pressure in the calculation of gas law. In our next class, we shall continue on this calculation by looking at another phase where this can come up. If you really enjoy this class, kindly subscribe to my channel and click the notification bell for my subsequent contents. If you are our usual member, don't forget to leave a comment and share to your loved one. Thank you and have a blessed day.